Section 2.3 is computations of derivatives, and we have a rule that we get to use now in this section. And in particular, we're going to get to the point where we can talk about what's called the power rule. So what I want to show you first is I want to show you a list of basic rules, and I want you to think back to some things that you know from the section we just did on graphing. The first three pieces of this, or the first two pieces of this, follow this idea. All right, so the first one here says f of x equals c. So what this looks like on a graph is if I had a horizontal line, right? If f of x is equal to 5. What is the slope on a horizontal line? 0. Your derivative is 0. That's it. If you have a simple number, its derivative is 0. Now, we did this one a moment ago too. When we had x cubed, it became, when we had a cubic one, what did it look like when I did its graph? It looked like a squared graph, right? And when we had a squared graph, I drew it and it looked like an x graph. It looks like those powers decreased, right? It went from a power of 3 to a power of 2. When I took a graph of a power of 2, I drew the derivative and it looked like a power of 1. Well, that's not by accident. This rule, we didn't see all the details of this, but this rule has a decreased exponent. This n is now n minus 1. And the exponent that was in, it actually becomes a coefficient. We didn't see enough detail to see that piece of it. But that is what's happening algebraically if you were working on one of those problems. There's one that's sort of missing in here. Your book just didn't identify it, I guess, and that's probably why I didn't write it in here. But sometimes people sort of want to identify that when you have a constant function, like, well, you know what, let me draw it as mx plus b, just like you see lines. When you're looking at this equation of a line, and you're sort of recognizing in your mind that derivatives are slopes, what is the slope of that line? M, right? So when you have a line given to you, it simply becomes the slope of that given line. That's the derivative. Now you could sort of get there by using the power rule explanation as well, but we'll see it happen, and it's a very nice feature. The next two are sort of, you get, and you're kind of like, when you use them, you don't even going to recognize you used them. The next two are actually telling you that if you have a constant multiplied by a function, then you can simply have the constant multiplied by the derivative of the function. And I promise, I'll show you when we use them, but you're not going to sort of feel like you've done anything when you get there. And the last one example, last example also here, is very much the same way, right? You see something added or subtracted. Well, you kind of like to just do each of them sort of like they're independent and then put the addition or subtraction sign between them. And that is absolutely correct as well. So you can take each piece independently and do their derivatives, and then you can add the results of that together. Sorry, that's a derivative there at the end. Okay, so are you ready to see the beauty of these rules? Here's an example. We have x to the 7th plus 3x minus 4 over x. Now, the first thing I want you to recognize is that that 4 over x can be rewritten. How could you rewrite the 4 over the x to be a more helpful way with these given rules?
4x to the negative 1.
Perfect. Right? An exponent, a variable in the denominator can be written with an exponent of negative 1. This is actually really handy because now I can apply each of the rules that I had before. X to the 7th is that power rule. I have x to the 7th power, so what should I do with the 7? Bring it down to the front, and I rewrite the x. And what happens to the 7 where it was? It becomes a 6. Now look at that. I've got the addition sign that I just get to write from the constant rule at the bottom, right? The sum and difference rules at the bottom. I can just do the other piece of it. 3x is a line. What's the slope of 3x? It's 3. Now, as odd as it may look, this is simply another application of the power rule here at the end. I have a negative exponent. That's okay. I actually also have a constant here, 4. Well, the 4 just gets to come along for the ride. Nothing happens with him. He's just going to be part of my answer. But this negative 1 here is going to get multiplied then by that negative. So negative 1 times the negative 4 that's in front is going to become positive 4. I'm going to rewrite the variable x because it has a new exponent. what will be the new exponent? -2. Make sure you're subtracting, right? You're subtracting 1. It was -1 to start with. -1 minus 1 is -2. Your final answer needs to be written in the same fashion that it originally started with. That is to say, if it started right here in sort of a rational notation, you're going to write your answer in a rational notation. So my last part of this would simply be to rewrite this as 4 over x squared at the end. That's the only piece that's any different. Because I forgot to put this in there. Thanks, guys. Yeah. What do you think? Not too. Yes.
Where the exponent becomes -2, how do you get to that?
So the same way that you got this exponent from 7 to become 6 is you subtract 1. So you take this and you subtract 1.
Okay, that makes sense.
Yeah, it's just that when it's negative, it looks a little bit funny. Yeah. Okay, let's try another one. This one needs you to do something before you can apply any rules, because you did not have any rule that said what happens when you have something times something else. We will, but we don't have one yet. So what are you going to have to actually do in order to use the rules as they were given? You're going to have to distribute. You're going to have to do some little algebra, right? So we need some algebra to happen before we can actually finish the problem. Or really start the problem, to be honest. All right, so we're going to do the algebra. I'm going to take that x times 3x squared, which is going to be 3x cubed. I'm going to take that x times that -4, so I'm going to get -4x. I'll take that 1 times the 3x squared, so it gives me 3x squared. And then the 1 times the -4 gives me -4. I don't really like that they're not in order of decreasing exponent, but they're not wrong. It's okay to leave it that way. And you're not really done, though, because you haven't done what you've been asked to do. You haven't differentiated yet, right? All you've actually done is multiplied something out. So, but now that you've multiplied it out, you are ready to take a derivative. Now, if you could simplify, let's say, for instance, when you did this multiplication, 2 of these combined. Well, combine them, right? There's no reason not to combine them. None of these do. They all have different powers of x, right? So we can't combine any of those. But this has 3x cubed. So the exponent 3 will do what? It will come down and multiply by the 3 at the front to give me a 9. I rewrite my x with what power now? Squared, a 2, yep. -4x, that's a line, right? It's a linear rule. What's its derivative? -4, very good, right? The negative is going to be a part of it, but it's just -4. Next piece is the 3x squared. What's going to happen with the 2? Come down, multiply by the 3 to give me 6x. And it is plain old 6x, right? Power was 2, now the power is 1. What about the number at the end, -4? That's 0. So you don't have to write it. If you want to write it so that you remember that you actually did something, that's fine. You could rewrite these in order of descending exponent if you want, but you can also leave it that way, which should be fine. So far, so good? All right, this one looks different for a couple of reasons. Notice the example directions say, compute the indicated derivative. What in the world do you suppose d2f over dx2 means?
You need to get it twice x squared.
We're going to do, well, close. We're going to do the derivative twice. It's not actually because of x squared. This notation is a little bit funny to read, but what it actually says is I want the derivative, I want the second derivative of the function f with respect to the variable x twice. That's what it means. I'm going to say it again. I want the second derivative, that is, I want to do the derivative twice, with respect to the variable x twice. It sounds so much harder than it really is. So I'll use the notation simply because they started with this notation. The first notation is df dx. And it means I take this function and I take its derivative. Now, the x to the 6th is written just fine. How could I rewrite the 5th root of x to be more helpful?
X to the 1/5.
Very good. This is x to the 1/5. It's kind of like when I had that exponent or that variable in the denominator before, I pulled it up to the numerator with an exponent. Same thing here. All right, so the x to the 6th, what is the derivative of x to the 6th? 6x to the fifth. Everybody good with that? What is the derivative of x to the 1/5? 1/5. The 1/5 comes down. X to the -4/5. Where did -4/5 come from? 1/5 minus 1. It's subtraction, right? I know you don't maybe like fraction subtraction, but you'll survive. You guys are in calculus. I know you know how to subtract fractions. Yeah, 1/5 minus 1, which is -4/5. This is the first derivative, but I'm asked to find the second derivative. And all the second derivative is it's the derivative of the derivative. So we just do the same thing again with this one in the middle that we already found being my starting point. So what is the derivative of 6x to the fifth? 30x to the fourth. Very good. What's the derivative of 1/5 x to the 4/5? Good. -4 25ths. X to what? -9/5. Very good. I'm good with you leaving it like that. If you check to the back of the book, what they might do is they might do something like this. They might go ahead and put the fifth root back out on the outside and leave this as x to the 9th underneath. I'm sorry, I made a mistake. It would be in the denominator because it's a negative exponent. So they probably would write it like this, actually. I don't really care that you get this to this point. It's not a big deal to me. I just want you to recognize if you're trying to differentiate, did I get the right thing? Yeah, you did, if these sort of is where they're headed. Any questions on this one? Okay. This one's a little bit different question. It says, use the given position function. We talked about position functions in the last section to find the velocity and acceleration. All right, so velocity, we remember seeing that phrase instantaneous velocity? Do you guys remember that? Instantaneous velocity, slope of a tangent line, and derivative mean the same thing. So them asking you to find the velocity is equivalent to them asking you to find the derivative. And you now have a whole bunch of wonderful rules to do that, right? Any guess as to what acceleration might be? It's the second derivative. So this fancy question is really just saying find the first and second derivative, much like the last question did. The other thing that's interesting about this one is that it looks like I've got division going on in the problem, doesn't it? And you do not have any rule for division yet. We will, but we don't have it yet. So what do we do with? Well, we can do a little bit of algebra, just like we did on the problem that looked like there was multiplication. The first thing I'd like for you to recognize, you know what, let me do it that way first, is that how can I rewrite the square root of t? I'm going to write it as t to the 1/2 for now. Yeah, we could write it as -1/2, but I'm going to leave it as 1/2 and in the denominator. The second thing that I want you to recognize is that you can actually separate each piece of the numerator out and divide it by the denominator. That's sort of an application of what we do when we add fractions together, right? We get a common denominator and then we combine the numerators. And I'm sort of doing it in reverse. I'm sort of taking the denominator and I'm separating out all the numerators with that denominator. Is everybody good with that step? Okay, we're going to do one more cleanup step, and it's a property of exponents. I have 4t squared over t to the 1/2. How can I rewrite that? 4t to the 3/2. And where did 3/2 come from, Blaine?
2 minus 1/2.
Right. Rule of exponent says I can take the top exponent minus the bottom one. So 2 minus 1/2 would be 1.5 or 3/2. This one in the middle one right here, this t has an exponent of 1, right? It's nothing there, so it's an exponent of 1. So if I have t over t to the 1/2, and I subtract the 1 minus 1/2, I just have a 1/2. And then the last one has no t on top, so I will simply have to move that back to the top then. And it's coming up. It's negative because it was in the denominator. Now it's in the numerator as a negative exponent. All right. Let's finish the first derivative on this one, and then we'll pick up the second derivative next time. Did not get as fast as I wanted to today. My goodness. All right, let's do the first derivative. I've got it in a form now that I can do. The first derivative is velocity. So that's how I'm going to write it, write velocity. Or we could write s prime of t. It'd be the same thing. How do I take this 4, what do I do with this piece right here? 4t to the 3 halves. Yeah, 4 times 3 halves. What's 4 times 3 halves? It is 6. 6t to what power? 1 half. Very good. T to the 1 half will become what? 1 half t to the negative 1 half. And then the 3t to the negative 1 half will become, oops, yeah, negative 3 halves t to the negative 3 halves. All right, would you guys bear with me to let me finish the problem with the a of t next? It'll just take about a minute. Okay, a of t, same thing. I just need the derivative of what I just found, the derivative of this piece. 6t to the 1 half, what will that become? 3t to the negative 1 half. Negative 1 half t to the negative 1 half, what will that become? Positive 1/4 t to the negative 3 halves. I think you guys might like fractions a little bit. And then I have negative 3 halves t to the negative 3 halves. Positive 9/4 t to the what? Negative 5 halves, that's right. Very good.